No questions. Okay, let's go to Rohini. Make sure that you stick to time, because otherwise we are gonna to schedule.
Sure, definitely. I'll just share my screen once again. Okay, can you see my slides?
Yes.
Great. Okay. Okay, so just one thing. So before I begin, so I'm just sharing the link for these slides. So if anyone has any questions, wants to go back, so please refer the link. It has the PDF version for the slides. So now we'll begin. So hello everyone, my name is Rohin. Hope everyone's doing great. I'll be presenting SimCLR, which is one of the state-of-the-art algorithms for self-supervised learning. Before I begin, I'll be going through some acronyms because we'll be talking about these over and over, and so that I don't have to say the entire name again. So SimCLR V1 is the name of this paper. DRLIM is one of the seminal papers on contrastive learning for self-supervised learning. It was by Raya Hasdale, Sumit Chopra, and Jan LeCun in 2006. It is the one that started contrastive learning with images. Pretext task is something which Sayed already explained. It is like a toy experiment that we make the neural network play so that it can learn some interesting latent space representations. Downstream task is the one that you really care about. You can think of it as like a transfer learning, but it is really the in context of self-supervised learning. SSL will be self-supervised learning. CL will be contrastive loss or contrastive learning. SL is supervised learning. State of the art. NCE is the loss function that SimCLR uses. Is called noise contrastive estimation. And NTZent is NCE with temperature coefficient. So it's like just a temperature parameter, which you again might have already seen previously. Okay, so we saw this previously. Self-supervised learning is really pushing state of the art in machine learning for vision and also other modalities. Also around like just 2 months ago, Facebook AI released their new library for self-supervised learning, which is called Whistle, and it has like all the implementations from recent algorithms in self-supervised learning, SimCLR, Moco, Swave, all the state-of-the-art algorithms, and this is really to democratize and make self-supervised learning accessible to everyone. Also, just 2 days ago, I saw this old blog post in which Tesla Autopilot is using self-supervised learning for their vision and perception. So it is actually being self-supervised learning is really being used in production already. And the key algorithm driving this is one of the key algorithms driving all of it is we'll be discussing today. So hope you are excited about it. Okay, so contrastive learning. So we already saw this. So it is contrastive learning is essentially trying to bring similar images closer and dissimilar images farther apart in the latent space. And the seminal paper for this was DRLIM, dimensionality reduction, in 2006. So it actually dates back long ago. It's just that recently we have started using it for neural networks much more extensively. So we saw this previously. I'll consider the very last third image. So consider blue points, which are similar, like similar images, and all the colorful points, all the other color points, which are far apart. So we are trying to make them farther and the blue points closer in the smaller latent space that are encoded network points. This is the visualization by DRLIM. So this again, going back to 2006, and in purely unsupervised manner, it is automatically able to cluster these different MNIST images together. So all the 9s are together, 4s are together. This might look a bit like T-SNE if you have seen it, so fully unsupervised, and it is able to find some latent space representation, which automatically clusters similar objects together and dissimilar objects farther apart. which is what essentially contrastive loss is trying to do. So this is a typical self-supervised learning pipeline. In the first stage, and yeah, I mean, I want to make this interactive, so if you have any questions, please feel free to stop me at any point. So the first stage is the pre-training stage. It can be a pre-text task or contrastive learning. So that is the first head. So you have some pre-text tasks, some jigsaw or colorization, rotation, anything, or contrastive learning. So you train the network on fully unsupervised data. You have no labels for it. The blue and the yellow part are two parts of the network. So blue part is generally the encoder, and yellow part is generally some head you put on top of it. It is generally a MLP. Different papers have different implementations. And essentially, once you are done with training, you take your encoder part, the blue part, and then you transfer it for your actual downstream task. And for the downstream task, you have the actual labels, and then you fine tune it by applying again, a MLP or a classifier head. It can also be a regression head, which is shown by the by the red network. Okay. So this paper's name is essentially a simple framework for contrastive learning of visual representations. So you might think, what is really simple about this? Why is it called simple? The reason it is called simple is because it uses just contrastive learning and nothing else. So previously in Sayyed's presentation, you saw it was using a memory bank. And if you read about self-supervised learning literature, you will see many use fancy architectures. This paper uses just contrastive loss and nothing else. Now, the key ideas in this paper are, as I mentioned, contrastive loss to make the augmented versions of the same image closer. So you take an image and you augment it. Many data transformations are possible. Since they are essentially the same image, the augmented versions should be same, and that's what you make the neural network predict. And all other images in the mini batch are considered as negatives. And just on top of this, you put on some standard neural network tricks, and essentially you get state-of-the-art result. One of the key results in this paper is, before I go into the paper, one of the key results that I want to highlight is that SimCLR does on par with supervised network, with supervised learning of ResNet. So I have circled 2 data points, which are the main ones that you should look at in this figure. SimCLR, which I'm pointing with my laser pointer, is on the right, and on the left is supervised. Both have same backbones, so both are ResNets. The ResNet on supervised has full labels of ImageNet, and it reaches around 76% accuracy. SimCLR has been pre-trained on ImageNet, and on top of that, there is just a linear classifier. And with just the linear classifier, which sees the labels, it is able to get same accuracy. And I'll be going into a lot more detail into this result later on, but just to give you a foreshadow that this is really powerful technique. A small caveat in this slide is that if you notice, the supervised uses just 25 million labels. SimCLR 4x uses 400 million labels. So it's like almost 20 times, parameters. So it's like almost 20 times more parameters. It is really over parameterized, and that is a general trend we will see with SSL. So now SimCLR at a high level, your input image is X. So you take in any image and you pass it through some random data augmentations. So imagine you have a augmentation kit which has 10 augmentations possible. You randomly sample 2 augmentations from it and you apply it to your images. That creates 2 new image pairs for you, which are the positive pairs for contrastive loss. Since these are essentially the same image, therefore they should be the positive pairs. You want these 2 augmented versions to be similar, and they are called XI, and XJ. On top of that, you have an encoder. In SimCLR, the encoder is a ResNet, and I'll be again talking a lot more detail into encoder soon. So imagine you have these 2 augmented versions. You pass it through some encoder. You get some latent space representation, which is HI. here the latent space representation is nothing but the final output layer of the ResNet. So before the average pooling. So it can be a 128 or a 256 dimensional vector. That is your latent space representation. And on top of that, you put a MLP, which is the G function. Basically, it's just trying to transform that latent space into another smaller representation, which is the Zi and Zj. Essentially, now Zi and Zj, if they are coming from the same image, you want to make them similar. And all other images in the many batch, you want to make them dissimilar, which will be enabled by the contrastive loss function. And this is a SimCLR, again, just another view, very same. You've taken an input image, augment it. The first image has been colorized, the second image has been rotated, but essentially I still want the neural network to make them look, to make them predict as if they are the same images. Pass them through an encoder, which is a ResNet 50, get some last latent space outputs, pass it through some MLP, get another smaller vector, and then pass it through the contrast loss. This is what your entire data set might look like. So you have n images, all are transformed into two versions, which are random augmentations. So given n images, your data set becomes 2n. Every image is transformed into some random augmentation. And this is another visualization showing SimCLR again. Dog, which is coming from the same image. It has some random augmentations. It flows through the network, and the dogs will be made similar to each other. So later in the latent space, they'll be brought together closer, and the chair will be brought closer in its own, and the dog and the chair would be made farther apart from each other. Okay, please feel free to stop me at any point. So this is the NC loss. We already saw it in Sayed's presentation. Essentially, on the numerator, you have the positive pairs. In the denominator, you have the single positive and all the negative pairs. Yep. And you want to train your neural network to minimize this NC loss. So it is similar to, you might have a softmax or any kind of loss function. We are using NC loss function over here. And a small caveat here is that, you have a mini batch of, say, size n. You take in a single image, you augment it, you get a positive pair, and you're considering all the rest of the n-1 images in this mini batch as negatives. Whereas if you had the ground truth, if you had the two labels, you might see that is not true. So the rest of the n-n images can be similar from the same class as your image. Right now, we do not have the labels, so we are just assuming that they're all from different classes. So this is actually like a weakness of entire contrastive learning, but still it turns out to do really well. And just to maybe just have some intuition, you're not just trying to bring similar images and dissimilar images further, but you're also trying to learn something inherent about the images. You're not just trying to learn classes, but you're also trying to learn images that, yes, these are 1,000 different cats, but this specific cat image has been augmented, and these two augmented versions are from the same image, and other cat images are actually different, even though they belong to the same class. So I believe it is trying to learn some richer latent space representation. This is again like just a guess. And this is the final loss function that SimCLR actually uses. It is exactly the same as NCE, but it has a temperature parameter. Temperature parameter actually just changes your distribution. So if you look at the NCE loss function and you just tweak the temperature parameter, your distribution just contracts or expands, as you might have seen with general probability distributions. And by tweaking this temperature parameter, your accuracy improves basically. So it becomes another hyperparameter in your entire pipeline. And it is really worthwhile to look into what is this loss function really trying to do. So consider the numerator. basically consider the first line, that is your loss function. You're trying to minimize it. If I bring the minus sign inside, the numerator denominator flip. Now the numerator essentially has a single positive pair and all the negative pairs. The denominator has the positive pair, and you can actually basically divide it by the first term, and it becomes 1 plus all the negative pairs upon the positive pair, and you are trying to minimize this. So minimizing this means that you're trying to minimize the numerator, which is all the negative pairs. So whatever similarity metric I have, which is like a cosine metric, in the cosine laws, I'm trying to make all the negatives smaller. So all the negatives should appear. Sure, the neural network should be able to predict that all these are negatives and they have a smaller score. And then I'm trying to make the denominator bigger. So after the cosine loss function, after the similarity metric, I want the positives to become larger. So what I'm trying to show here is that the loss function is actually doing what you really intend to do. Another small caveat here is that this loss function is asymmetric, very much like a KLD divergence if you have seen. So it's not like f of a b is same as f of b a. And the reason is because the denominator, it compares a single image with all the negatives. When it is doing so, it is doing one augmented version with all other negatives, and in the second case it is considering the other augmented version with all other negatives. And you can imagine these are essentially two different things, which is what the final loss function actually captures. That I have first augmented version and I compare it with all the other negatives, and the second augmented version, and then I compare it with all the other negatives, and then I just average that over the entire data set. And this is the main algorithm. It is exactly same as what I just explained. The implementation is really simple. Now, some neural network tricks that made it really work were that as I'll be going further ahead, you'll realize that SimCLR really benefits from larger batch sizes. So the larger your batch size, the better it is. And on a typical GPU, you cannot fit really a lot of images, maybe 256, 512, not more than that. And over here, they were using 16,000 images in a single batch size. So you need really large optimizers. So there has been a lot of research on just optimizing with multi GPUs and large networks. So there's something called as large optimizer, which really stabilizes the training, and that was used for these experiments. And they had 128 TPUs, and it was trained within 1.5 hours. So it looks training time is really small, but 128 TPUs is a lot. Maybe a single TPU is like maybe 10 V100s, so it's like 1,000 V100s. So we have V100 on Discovery cluster if anyone wants to use. So it's like maybe 1,000 V100s in one go, which is a lot. The second trick was extensive data augmentation, so this was a really key point, and it really made them get really good scores. And the final trick was global batch norm. So generally, when you're doing parallel data training, data parallel training with multi-GPU. So multi-GPU has like two kinds of trainings. It is model parallel or data parallel. I wouldn't be going into it. It's like another entire thing of its own. But if they were using data parallel, in data parallel, your neural network remains the same, but you are sampling different batches, mini batches, and passing through the GPUs, many GPUs. Now there's some locality. So certain GPUs have certain informations. Generally, you can just aggregate those batch norm, mean, and variance locally per GPU. But over here, you can imagine that our data is asymmetric. Maybe a single GPU will have the positive pair, and rest of the GPUs would not have that positive pair. And basically, the data distribution is really asymmetric. And this is maybe a really nice learning that, in future, whenever you have asymmetric data distribution, you really want to globally find the batch norm, mean, and variance for accuracy of the algorithm. So that is called global batch norm. There are some other ways to deal with it, which are called layer norm, or basically another way which you can refer the paper for. Layer norm is another way, but this paper used global batch norm. Now evaluation. So for evaluation, they used the linear evaluation protocol. That is one way. And then they also compared it with semi-supervised learning and transfer learning. And it's really worthwhile to understand what does really linear evaluation protocol mean? And this you must have heard of in previous MOCO and ingest presentations as well. What it really means is that you freeze your encoder, you do not train it, you do not expose it to the labels. So the encoder has only seen the untrained, uh, has only seen unlabeled data. On top of that, you put a linear layer. So linear is actually really simple, right? That it is not sophisticated, just a simple MLP, maybe with really non-linearity, but nothing else. And you just show the labels to the linear layer. By doing so, by putting a really simple linear layer on the end, you are really trying to see the power of self-supervised learning. Because if you were to engineer the final layer, then basically engineer the final layer and really expose that to labels, then basically you're not evaluating it well. So for proper evaluation, you want to freeze the encoder, do not expose it to the labels, and put a really simple network at the end, and then just show the labels to that network, and then see how well is it doing. So this is our, and I'll be going to linear evaluation protocol results, which are really exciting, and that is the real takeaway from this paper. Experimental settings, as I mentioned, ResNet is our encoder, a simple 2 MLP as a projection head, NT-isn't loss function, loss optimizer. 4096 was a simple batch size, but they extended it to 16K as well, and some linear warm-up first and epochs, cosine rate, scheduling without restarts. As I mentioned, data augmentation was a really key point of this paper, or that really got the accuracy really high. So a really nice thing about this paper was that they did ablation study, that what if I keep just one data augmentation and then I apply the other. And since there were about 7 of them, it makes like a 7x7 matrix. They tried out all the 49 combinations. What is the one that works out the best? And turns out the ones which are really yellow or whitish, that is 59 and 55, they are the best scores. And they both correspond to the same thing, which is color and crop, which means you do a random crop and then you do a color distortion. And this is the data augmentation that gave them the best result, which they used for their all other experiments. So when I said random data transform, you can imagine they're always doing random crop followed by resize, and then random color distortion. And this was now we are coming to the experiments, the results. Uh, what this slide is showing is that the more they do color distortion, the more better the accuracy becomes. So color distortion really helped them in getting a really good number. An interesting thing was there is an algorithm called AutoAug, which is a really famous algorithm. And you can see AutoAug pushes the supervised result really well. So in the last row, AutoAug gives the best result. So AutoAug is a way of doing augmentation. AutoAug works super nice in classic SL. It gives 77.1% best score. AutoAug does not work with SSL. And really simple color distortion is what really gives them good results for self-supervised learning with MCLR. Now coming to the encoder. So what if we play around with the encoder, and what does a good encoder look like? What this slide is showing is that you consider a ResNet. So this is a result which you might have seen many times, that you make the network deeper, results improve. You make the network wider, so not just deeper, but increase the number of filters. That is what 2x and 4x mean, that you increase the number of filters in every layer, and the network accuracy keeps on increasing, which is also fine. But the key thing that this slide is trying to show is that self-supervised learning benefits a lot more than classic supervised learning. So consider the green points. As I make the network wider, so 1x, 2x, 4x, self-supervised learning might have improved like 1 to 2%. Now consider all the other data points which are really SSL. They improve drastically as you make the network wider and deeper. So their takeaway was that self-supervised learning benefits a lot more from deeper and wider networks. Now coming to the projection head, they did some experiments with what if I keep a simple MLP, what if I keep a nonlinear MLP with really nonlinearity, and finally, what if we just keep an identity function and nothing else? And as you might expect, nonlinear MLP is the one that gives the best results. This is the final projection head, and just for sake of global overview, encoder is during the pre-training, projection head is during the pre-training, but the final head for the contrastive loss. They also experiment with the different loss functions. So I've been saying they used NT-Zen, but why do you use NT-Zen? Why don't you use other loss functions? And this paper actually tried out a lot of different loss functions. And after a lot of evaluation, turns out NT-Zen was the one that gives them best results. And if any of you have read word to X paper, NT logistic was the loss function used in word to X. So word to X is another classic paper that basically really, brought this kind of random sampling of softmax into the picture. Another seminal paper. So that paper used NT logistic, and NT logistic worked okay for them, but NT Zend worked even better for SimCLR. And maybe it might be worth revisiting. What if we keep NT Zend in what to work and see how the performance is now?
Joaquin, you need to finish soon.
Yep, I'm coming towards the end. Now there are experiments with increasing batch size and training time, and we see that improving batch size and increasing the training time keeps on increasing the results, which is really contradictory to classic supervised learning. And I'll be coming towards that towards the end in future work for this paper. This is the linear value share protocol, which I said was the main result of this paper. That consider the very last row, that is ResNet 4x, 76% accuracy. This result for ResNet, fully supervised, is also 76%. So ResNet is a really sophisticated model. It has seen, and if you train a 4x version of it, fully supervised, expose it all of the entire encoder decoder to the labels, that's how you can get 76% accuracy. And over here in the last line, just the encoder is seeing fully unlabeled data, and just the final linear layer is seeing the label data. So just by showing the final linear layer, the label data, it is able to get as good as ResNet. So in a way, you are really comparing a linear MLP, which has seen the labels, and an entire sophisticated ResNet architecture, which has seen labels end to end, and they get really same accuracy. So which is really interesting. There are also experiments with self-supervised learning, which I'll just skip over, but they are also really interesting. They also did experiments with transfer learning, and again, basically the key takeaway from self-supervised learning and transfer learning results is that this paper really pushes state-of-the-art results over classic supervised learning methodology that people had been using since a long time. And finally, there was also a follow-up called SimCLR V2 in October 2020. And the key finding was that as you scale the model, scale the data, you get better results. So just increase the model size, get more data, and the results keep on increasing. And this result is in line with other state-of-the-art results in other SSL methods, which is MoCo V2 and CPC V2. All of them just scale the model further and further, more data, and results keep on increasing. And this actually reminds me of the beta lesson by Richard Sutton that you can have some high-tuned features, but eventually leveraging, you just throw more and more computation, and basically you get better results. And that has been a general trend over the past 50 years. A main drawback of this paper is that it scales with batch size, and no one has 128 TPUs. So it is really unfeasible to have that kind of computation budget. Further, as you do multi-GPU training, it becomes really sophisticated to train them well, or efficiently, because you need to have knowledge of as I said, Lars optimizer, and a lot more about multi-GPU training, and it can be a steep learning curve for a typical vision researcher. An alternate to this is Moco kind of approach, which uses momentum and it does not need big batch sizes. And it can still work well, but as Moco V2 also scaled out to a lot of huge batch sizes and huge models. So we are really SSL, it really scales with batch sizes and bigger models, more data. So more computation budget definitely helps. A related work that I think in last presentation, I think Alan pointed out was what about adversarial robustness. So I just wanted to keep it over here. This was the review paper for review paper 1. And this talked about, the first paper talked about adversarial robustness with pretext task. And below, the same authors came up with another paper which used similar adversarial robustness with contrastive learning. There have been a lot more related work, as I mentioned, MOCO V1, V2. These are acronyms for other research papers. And all of them have been implemented in Facebook AI's Whistle library, making SSL more accessible. There has been a state-of-the-art result just this month, which is called SEER, SEER. It's another paper which really combines RegNet architecture with SWAV. So as I mentioned here, SWAV is another SSL algorithm, and you combine it with RegNet, which is really an AutoML kind of architecture search for encoder. And that is really the state-of-the-art result in SSL today. And they pre-train it on 1 billion random Instagram images. And there was actually news about it that, like, do you have Instagram images approval for doing this kind of training? So yeah. So this is the state-of-the-art result as of today. The key thing again is that you just have a lot more images, a lot more data, and your results keep on increasing. SSL really says that they have 84.2% accuracy using 1 billion Instagram images. And then it compares it with SimCLR, which is say 83%, which is so like a 1% improvement in performance. But you also see that it has 1,000 more images. So it's like, it may not be a really fair comparison. SimCLR ImageNet had 1 million images. Seed had 1 billion images, so 1,000 times more. And it gets just like 1% more accuracy. So maybe if someone scales SimCLR V2 to 1 billion images, maybe it could have got similar accuracy as well. Also, if you notice, the parameter size is double. So Seed uses RegNet architecture, which has, again, double the number of parameters. Another related work which I did not explore was self-training with noisy student. It is again by Google Research, and it's on similar themes that you bring in self-supervised learning to your supervised learning pipeline, and you can really push state-of-the-art results. Future work that can be explored is, what if we make AutoML meets SSL? So just to give you a background, this is a bit older slide. I put it in my project proposal, and basically Facebook actually did it with CH. So RegNet is AutoML with SSL. So this actually works. The reason I put it out there was that ResNet is just a standard architecture that everyone uses because it's commonly used in literature, but there wasn't any AutoML search with SSL. So SSL has a different optimization objective. And if you throw in this optimization objective with AutoML, which can use a neural architecture search to find good architectures, it can really improve the performance. And turns out, yes, it does. So another future work possible is, what is a theoretical basis that why does SSL improve with increasing batch size? This is contradictory to classic supervised learning. So in general supervised learning, you can have a full, like 1 million images gradient descent, which is like an actual gradient descent, but it is not possible to have that on like GPUs with 10 GB RAM. You can have a single batch, like a single example GD, which is the SGD, but it is not the true gradient. So we generally go with a mini batch GD. It actually brings in some noise to the network and helps in training. And that is what we learn from general supervised learning, that the noise that mini batch GD brings in, it really helps in training, because increasing the batch size with typical SL sometimes hurts performance. This is not true with SSL. So in SSL, you keep on improving the batch size and your performance keeps on increasing. And we really don't know why it's so. So there is some scope of theoretical basis for this observation, and it may actually reveal something interesting about the properties of training neural networks. And finally, the final future work I think possible is that as we are seeing, neural networks are becoming bigger and bigger. So maybe it would be time to like bring in quantization and pruning literature into the field of vision. So generally, pruning and quantization is used for the edge devices, for really small, like tiny ML kind of applications. But it is, and it's like an isolated world of its own. But we haven't seen that kind of research being leveraged by vision community when our models are becoming just huge. So I do think it will definitely help a lot, because these techniques can help the network become 10 times smaller without hurting accuracy. So imagine you are getting 10 times the GPU budget without accuracy, without hurting accuracy virtually. And my prediction is that field is moving really fast. Yeah, like there are new results every 3 months. And I believe that in the future, SSL will become integral part of all pipelines to push state of the art in different modalities. And it is already being used by some companies like Tesla Autopilot in production. Yeah, these are my references. Thank you.
Okay, thank you very much. Sorry, we won't have time for questions though, because I need to cover the slides for today. But thank you. It's a very interesting topic, and I know why you are very excited about it. I hope people enjoy the presentations. Okay, so let's see if I can share my screen now. Can you guys